Okay, so today we're going to finish off the sample problems. All of these sample problems end up revolving around the concept of the conservation of energy. Okay? The way in which we take this approach, we do take the approach that there is no friction to consider at this moment. Again, it's going to be a little bit later, like once we get into our labs that we're going to do towards the end of this week, that we start to introduce the concept of how does conservation of energy really work when we do take into account frictional forces. So, okay, we kind of did our bowling ball pendulum problem for homework due for today that we just checked. So let's kind of go ahead and take a little bit different approach to some questioning based off a similar type problem. So here we go. Student demonstrates conservation of energy by releasing a 5-kilogram ball attached to a 1.5 meter long rope. Okay, we know the ball has 73.5 joules of potential energy when it is released. Okay, we want to know how much kinetic energy it has at the bottom, what the ball's maximum speed during its swing, and at which point should we swing the ball if it's going to strike a building and maximize damage, as if we're using it as a model. So, let's get a pen here, red it is, I guess. Okay, A, how much kinetic energy does it have at the bottom of the swing? I think this is a pretty easy question. So, what would the kinetic energy be? Should we go the whole route of 1/2 mv squared? No, well, we don't know the speed at the bottom. Do we need to go the whole work energy theorem route? No. Okay. Do know, okay, that the kinetic energy at the bottom of the swing, are we at all kinetic energy, maximum kinetic energy at that point? Yeah. Okay. The question we have to ask ourselves is this. At the top of the swing, did it start from rest? We're assuming by it being released and not pushed, then yes. So at that point, at the bottommost point, how much kinetic energy should it have?
73.5.
Yep, the 73.5 joules. Okay, and I'm okay with us just stating that at this point. Okay, if it is 73.5 joules of potential energy at the top of its swing, released from rest, 73.5 joules of kinetic energy by the time we get to the bottom. Okay, now in part B, now we're asked for, okay, what is the ball's maximum speed during its swing? Well, at what point do we get maximum speed? At the height of 0 in the system, yes. Okay, the lowest possible point in that system. Okay, which is what we just found here. Kinetic energy is 73.5 joules. Okay, so when we go ahead to rearrange this, 1/2 mv squared for velocity, pretty easy stuff, and we have done it before. Okay, square root of 2ke divided by m. Well then, pretty simple pluggy chuggy, square root 2 times our kinetic energy of the 73.5 divided by the mass, which we're told is what? 5 kilograms. Okay, nice and simple pluggy chuggy. Go ahead and find what our maximum speed is going to be. Alex, when you got an answer, let me know. .422 meters per second. How many of you, by show of hands, would agree with Alex's response? We certainly should. Okay, roughly 5.5 meters per second for that. Okay. All right, part C. We'll just kind of chat about this one. If this is kind of a small-scale model of a wrecking ball, at what point in the swing should we be at for that wrecking ball to maximize its damage? The lowest height that we can get within our system. Okay? Now, realistically, it's going to be very hard to pull that crane up right to the edge of that wall. Okay? And in order for actual safety, they actually prefer for that to have a slight upward swing to that so it actually pulls away from the building once it's done. Okay? But if we're just talking about maximizing the damage of that, Yep, should absolutely be at the point that it has the greatest speed, okay, and that's going to be at its lowest possible height. Cool. Next problem. Okay, the Millennium Force at Cedar Point in Sandusky, Ohio is one of the tallest giga coasters in the world. The first drop is 94.5 meters straight down. Assuming the 400 kilogram roller coaster starts from rest as it crests the top of the first hill, which I know is not necessarily true, we're going to find the speed of the riders at the bottom of the hill. Okay. Now, let's just have a quick chat about this. How are we going to solve this problem? What's the first thing we're going to have to find? Find what? Potential energy where? Okay, potential energy at the bottom of the roller coaster. What's the potential energy at the bottom of the roller coaster going to be? Would the potential energy at the top help us? Absolutely. Okay? Now, in this problem, which is not necessarily a direct reflection of reality, it's saying that we start from rest at the top of the hill. So we know all of the mechanical energy would be stored as potential up at the top of the hill. At the bottom of the hill, is that going to get converted to kinetic? Absolutely. So here's what I'm going to have you do. I'm not going to put it up on the board. Okay? I'm going to have you guys do it as we kind of go along and break this into two parts. First part is we need to know what the potential energy is at the top of the first hill. Okay? So one, we'll find that. Two, then we know that that amount of energy is converted to kinetic at the bottom. And then just like in our last problem, if we know the kinetic energy, we can go ahead and solve for what the speed should be. So, let's all do this. We're going to do it on our own. Elson has already so graciously volunteered for his part, which is to put the potential energy part on the board. And then he has so graciously volunteered Anush to put up his part, which is going to be the velocity calculation at the end. Thank you, gentlemen. We kindly appreciate your cooperation. Volunteerism at its best. That is a 370440 joules.
Yeah.
It's okay. We now know what it is.
We have to find the velocity. The kinetic energy.
Okay, so let's check out what we got here. Our final response, thanks to our two fine gentlemen's answers, gives us 43.037 meters per second. Do we agree to it? Okay. Quick mental exercise has nothing to do with the problem. I want to see if you remember how to do this. Convert that value to miles per hour. Just your friendly reminder that when we do that conversion, we should be getting slightly more than double. If we've done it that way, then there's a good chance, assuming we've used our right values in the right part of the ratio, we've done our conversion correct. Alicia, just for kicks and giggles, what is that expressed as miles per hour?
I thought 96.292.
Absolutely, 96.292 miles per hour, which, if we actually were to measure the speed at the bottom of that hill, we actually would come to find out it does not reach 96 miles an hour. And in addition to that, the actual roller coaster starts at some speed at the top. It does not start from rest. So it actually has even more energy at the bottom of the hill. So why is it we get an overestimation of our speed? Well, the reality is, okay, what we would observe is going to be less. Okay? So why is it we've said it? Friction. Think of all of the sources of friction. As this coaster cuts through the air at a 94.5 meter drop, is it going to encounter some significant air resistance? Yes. Okay? Is there going to be resistance between the car and the track? Yes. Okay, there are some forms of energy loss on this. Okay? Just know this is the starting point for us to then have that discussion. We can then work our way backwards using the energy approach when we're ready to introduce that concept. I just want to go ahead and put that there. Okay? Now, here's what we're going to spend a little bit of time today doing. Okay? We've built up a little bit of our understanding of kinetics, potential, and really how this is going to influence something like a roller coaster problem. Okay? So, still treating this as a frictionless example, we see a mock-up of a roller coaster here where we have several different heights. And you can see we're going to take a look at 4 different points. That is position 2, which is top of the first hill, 3, which is the bottom of the first hill, 4, which is atop a loop, and position 8, which is some hill later on the track. So, here's how we're going to approach these problems. Just like with what we did with our bowling ball pendulum, we're going to take a look at what we have. I'm going to zoom in a little bit on this. And we're going to start here at position 2. Before we get started, let's look at it. Do we have a speed at position 2? Yes. So we have kinetic energy. Do we have height at position 2? Yes. So we also have potential energy at that point. We'll need to find that information. Now here's one thing that we are going to change a little bit for these roller coaster type problems that was similar to your bowling ball pendulum problems. On these type problems and these type problems alone, you will not be showing all of your calculations for it. Okay? Your data table is simply going to be your means of providing responses. Okay? So, here's what I want all of us to do. We know the mass of the coaster as it's given out here just to the side of our image. And we know what that speed is. Everybody using the calculator that you have in front of you, let's calculate the kinetic energy at position 2. And Emily, when you got it, let us know. 19,624.9 joules is what we should get for that. Okay? Good. Let's find the potential energy at that height. Justin Hampton, what do we get? Sorry, didn't mean to put pressure on you. When you're ready, go ahead.
610,050.
Monkeys, bananas, joules. Okay, now, this part should be very easy for us. Okay, we have potential, we have kinetic. What do we need to do for mechanical energy? Add them up. Pretty simple. Take what we have, 19,624.9. Add that to our 610,050. Gonna get a large number, but that's okay. Paige, what do we get? 4.9 joules. Absolutely. Okay? Now, for all of these problems, once you have the mechanical energy, you have the mechanical energy. So we will write out again 629,674.9 joules. 629,674.9 joules. Talbot, can I just do a drop arrow? No. Okay, we're going to list it out. You're going to show that you know that that value remains constant over the entire problem. 629,674.9 joules. Okay, and then back up to our velocity. Should we use our kinetic energy, reverse engineer what it is? No, why not? It's a given in the problem. And what is it? 8.86 meters per second. Life is good when we're given that in the problem itself. Okay, so here's what I'm going to have you do now. Okay, we'll kind of talk a little bit through the next step, but I think we can pretty much put it together at this point. Okay, when we get down to position 3, we're now at the bottom of that first hill. What's our potential energy going to be there? 0. We can then kind of figure out what our kinetic. We can work backwards to find the velocity. Okay. Then for position 4, we are atop the loop. Okay. Be careful with it. We're given a radius of 3.12 meters. I think that's what it says. I'm sorry, 31.2 meters. So what is the height at the top of the loop? Okay, 62.4. So this is the radius, and when you get all the way up to the top, you need to double that to get to that point. Okay, and then later at position 8, we're given the height that's there. Here's what I'd like for you to do. Go ahead on your own. I'd like you to try to finish out the rest of this problem. It's kind of a puzzle now. Okay, we have certain pieces of information. Let's go ahead and try to fill it in and get what we need. Yeah. They might be over there if they're over there. that are coming up and putting up their responses. Just kind of, we'll wait until we get it all together, and then we'll have a quick chat. Again, just as we're kind of finishing up, just keep in mind, okay, what's happening as we go from one point to another, okay? Are we decreasing our height? Okay, certainly if that's the case, we know our potential energy should be going down, right? And at the same time, as we're losing height, we should be gaining kinetic energy, gaining speed, okay? Vice versa. The higher up we go, we're gaining potential, we're losing speed, losing the kinetic. That's our quick way of kind of going through a quick check as to what's happening from point to point. Okay, so let's just take a look at what we have so far. Position 3 kind of helps you out with potential and kinetic. Gives us a speed of 50.187 meters per second. This would be a hill that is taller than the Millennium Force problem that we just did in the last problem. So should we expect that we're going to have a greater speed at the bottom of that hill? At least in theory, it's what the conservation energy would tell us. Absolutely. Okay. Then at a position 4, if you want to think of it this way, that's pretty close to about halfway back up from our initial height. So as you take a look at your potential and kinetic energies, aren't they roughly half of what they are in terms of the total mechanical energy? Yeah, pretty close to it. Okay. And then our speed, okay, 35.995, certainly going to be a little less than what we had at position 3. And then as we get to position 8, okay, we have a smaller hill there. So smaller potential energy, greater kinetic. I think as we're going to find out in just a second, okay, our velocity then is going to be a little bit greater than where we are at position 4. Okay, and while I'm going to give Allie a minute with that, know that when it comes to roller coaster design, you're going to see a pretty similar format for most roller coasters. Where is your biggest hill going to be? It's right at the beginning. And the same as you're designing your roller coasters as part of your project. Okay? Where should your greatest height be? Probably your starting point. Okay? Certainly, and with what most of you have at your disposal, okay, you don't have the option to use machinery or magnetism or anything else that's going to help you to get more energy into your system. Roller coasters kind of have that they can do that at certain points, but your largest hill certainly has to be your first. Okay? And then you have to kind of carefully manage your energy as you go throughout the coaster. And we go down our very large hill into our first loop. Okay? Are there things nowadays that roller coasters have to kind of help them out in certain ways? Yeah. Do you have the electromagnetic propulsion type ones? Yeah. Okay? They shoot you out at a very high rate of speed. Not necessarily needing a huge hill to crank you all the way up to get up to the top, but you're still going to go up to your greatest height right at the beginning of that coaster. Okay? The rest then, for the most part, is a gravity ride on your way down. Okay? Do we all agree with the 45.796 here? Okay, good. Okay, and in terms of our samples then, this is where we're going to stop for today.